recording. Recording in progress. Welcome everybody to our second shading and lighting lecture. Today we are going to be dealing with basic lighting. All right, so I believe I went over this in lecture 1, but we break our class up into rendering, lighting, materials, and textures. Okay, lighting is broken up into basic lighting, which is what we're going to do today. Then we've got a little more complicated lighting. We're going to get into still life and portrait. Welcome. What's your name? Kayvon. Okay, good. So sign in, get going. Sign into Zoom. Sign into Zoom so you can, get the slides on your computer if you want. I mean, you don't have to technically, but it's going to make it a little easier.
I would love to, but I had some difficulty last time.
Okay, remember, if you can't attend the live sessions, you have to watch the archives. They are in, I'm glad you brought that up. And I did send you a reply to your message. If you go into each activity in FSO, right here. All the lectures are archived. The newest ones show up at the top. All right, so do you have the Zoom app?
I do.
Okay, good. So are you using, which link are you using?
I used the one that was in the course.
Okay, that should be the same one. The link is also inside each activity. Should be all the same link. If you go down here under campus Zoom lecture, that'll take you, and you use the one at the top that says Zoom lecture lab meeting right here. This button. Were you using this one? If you use this one, this will take you to the right place. The link underneath is a separate open lab that's for campus and online students. All right. So let's get back to basic lighting. So basic lighting, which we're doing today, still life, and portrait lighting, which we're going to get into on Friday. And then when we come back from spring break, we're going to work on environment lighting. And then we get into doing textures for a couple of sessions. That would be lab and lecture, both. And basically, from there, we move on to texturing. So materials for a couple of lectures and labs, and then we do materials kind of wrapping up the class. So environment lighting project 5, just to give you guys a heads up. Project 5 will become project 6. You're going to light an environment, then you're going to add materials to the environment, and then you're going to pick one of the environments and do full-blown textures on it. So project 6 becomes project 7. All right, so today, just basic lights and diffuse materials. And we're going to talk about what that means when we get to it. Your download is going to be project 2. SAL Arnold. There's a zip file. Inside the zip, you're going to get a little packet like you got with the first activity, which was a Maya project folder. You're going to get a Photoshop template folder and then some reference images. All right. So office hours, I will have office hours Thursday, which will be 10 to 4. That'll be Discord office hours. So you feel free to come in anytime in Discord. But obviously, if it's during lecture or lab, you should be asking us the questions, not posting them on Discord. And hopefully they're topical too, because really we want to make sure we keep moving forward. And then, you know, the in-between times is a good chance to get caught up on other stuff. Does that make sense? Okay. We will have a Zoom open lab tomorrow. Frank, our illustrious lab instructor, will be running it for campus and online students from 1 to 5. That is the separate link at the bottom of that page that we have with all the Zoom links. So, you know, it's optional. Obviously, a lot of you have, what is it, CA or you have computer animation portfolio too. So you might not be able to make it, but if you can and you need help, pop in. Or if you're taking a break in portfolio, just pop in, you know. Same thing with Zoom. All right, just a reminder, spring break is next week, starting Friday at 5 p.m. This Friday. We will be out of the office. So you guys get spring break and we're all taking vacation during that time. It's one of the few chances we get where everybody's out, so we take advantage of it. So if you don't think you can finish your assignments on time, ask for an extension ahead of time. That way we can take care of it for you guys. We won't be on Discord either, but Discord will still be open. We'll take care of any problems when we come back. Now, project 3 will not be due until the Sunday before we come back. So if you have any really big issues, we'll deal with them Monday. All right, so everybody have Maya 2020 working? Okay, good. And you should have the Arnold to Mental Ray Arnold to Maya plugin. And it should be 4.2.1.1. Good. All right, how about out there in the Zoom world? Anybody got any questions? Nathaniel, Marie, Jaser, Derek, Darian, Clifton, Brian, everybody good? As far as Maya working and Arnold working. Okay, awesome, awesome. Works great. Good to hear. Anybody did anybody use the Arnold rendering workflow doc? If anybody has any questions or comments on it, let me know if you find a typo. If you see something that either didn't work or isn't clear, let me know. That way we can fix it. It is a brand new doc. We put it together. We all read through it, but you know, the more eyes, the better. All right, so what did you find to be, well, first off, before I do that, anybody have any weird troubleshooting things that took you a while to solve? Feel free to ask. If not, that's fine. How about out there in Zoom land? Zoomlanders. All right, everybody. Yeah, what's that? You did a save as, and not an export.
No, say that, so that's gonna take it to the left.
Yeah, save as target, and it didn't give it to you?
I can find the column. And the-
Oh, you mean you saved it, but you couldn't find where it went? Ah. You know, you could always open recent, open it again, resave it somewhere else. Screenshots, you're degrading the quality. So be very wary about turning that in as production quality. Yeah. Okay, what did you find to be a good starting point for a production quality render? So out of all the controls that we had camera, anti-aliasing, and we had diffuse. We're not going to be dealing with any specular or transmission until we get to different materials. Right now, we're working on a diffuse only material. So what did you guys put for the camera anti-aliasing? What did you do? Okay, well, this is in Maya. When you render it, it's under, let's pull up Maya. It's in the Arnold tab, and the default is 3 for camera, and it's 2 for diffuse. And remember, camera is kind of direct light, minimum samples, and diffuse is really indirect light, bounce light. Those are the areas that are the noisiest in a scene. Okay, which one did you do at 8? All right. All right, so if you did 8 here and you did 6 here, the one thing you want to try to avoid, if you take note here, it says, all right, when you put it at 8, you get 64, right? Because this is the square root. So the square root, 8 is the square root of 64. So that's your minimum samples. That would be kind of, that's like the max, you know, high quality for that. Yes. The diffuse, on the other hand, is only 256. Or sorry, it's 2304. It probably took you a long time to render because I found the higher the camera AA, if the camera AA is higher than the indirect bounce light, it tends to really increase the render time, and you really don't get that much of a noticeable quality difference. Yeah. So usually what I'll say is start somewhere around maybe 4, and that'll give you 16. And then if you keep it to the power of 2, which would be 2, 4, 8, change the diffuse to 8, that gives you 1024 on the indirect, if that makes sense. And a lot of times you're gonna need to experiment. Like you can do 8 and 8 both, which I have done. So if I choose to do 8 for the camera, right, that gives me 64, but it gives me 4K on the indirect. Do I really need to have all that going on there? And usually what I'll do is I'll take a small piece, render it out, and then compare it with what I have in my render view. Hello, welcome. What's your name? Chanel. Good, welcome. There are outlets in the middle of each, in the floor. Yours might be behind you. There's also outlets on either side. And Great, welcome. All right, so Brian down here said, he said AA to 4 and diffuse to 8. Yeah, that's kind of my go-to. I'll do, if I'm doing a preview quality, I'll keep it at the Arnold 3 and 2. That gives me pretty quick results. It's noisy, but it'll give me results. When I go to start rendering, I might crank this one up to 4. And then I might try this one at 4, depending on how much indirect light there is. If there's a lot of lights, it's a big scene, that number might have to go higher. Now, today, we're going to be doing a much simpler scene. We've got basically a small scene with just a few items in it, and we've got one direct light. So the render time should be much, much less, even if you crank your render settings up high. But like I said, I mean, I kind of navigate to this, and then I'll try doing a quick, like little small region to render it out. And then I might throw the denoiser imager on there and see what that looks like. And then I might do another one with the camera AA at 8, and just to see what the difference is. Usually I'll notice it's twice as long to render and maybe not quite twice the quality. So you kind of have to weigh it. Is it worth the extra time for not much noticeable results? Now, if you've got time to burn, you don't care, you're going to bed, you're kicking off a render, sure. But if you got a deadline, that's what you kind of have to think of. Does that make sense? All right. So good job, guys. Sounds like everybody's got the gist of it. Not really, really super complicated to do. Any information need to be clarified? Anybody have any questions before we move on? So Nathaniel, Marie, Cantavius, Joni, welcome. Jaser, Derek, Darian, Clifton, Brian, Angel, everybody good? Questions? Okay, Frank helped you in lab. Good, awesome. All right. Brianna, did you drop out?
Oh, it kept kicking me out.
Oh, okay. All right. Well, as long as you're here, you can see what's going on. That's good. All right. So just a reminder, all the reading link, the links are inside each lesson activity. We're using Safari Books Online. Today, we've got some extra reading. We're going to pull from photographic books or books on photography, digital photography, because they've been lighting for a long, long time, much longer than we have in CG. In fact, photography kind of laid the groundwork for film and games as we know it. Storytelling through the eyes of the camera. So when it comes to lighting, they pretty much have it down. So we're going to pull a lot of information from them. All right, email, check your email often, check your messages often on FSO. Just a reminder, don't send me any attachments by email in case Full Sail quarantines the message, or email actually, not message. If you put it in an FSO message, I am guaranteed to get it. All right. Just a reminder, if you can't make the live Zoom sessions, or I should say, if you can't make the live campus sessions, make sure you make the live Zoom sessions. We're trying to run them simultaneously until everybody gets a vaccine and we all get back together. So we're going to be kind of doing this hybrid, trying to offer lectures, at least for now, see how they go. And then we'll probably gradually fold in the labs also. So right now, we're not sure how this is going to work because we're not sure how many students are going to show up, how often the rooms have to be cleaned. Space for everybody is always another issue. If anybody remembers being back on campus before, you know, classrooms were pretty crowded and we usually wound up having classes right after each other stacked up. So have patience, we'll work it out. Okay, so just a reminder. So when we go to grade your assignments, we've got the rubrics that we've got listed in the about for the class. And actually there's a rubric section in our syllabus, but we kind of have a mini rubric inside each activity. Like the very first project you guys work on, it was all about render and quality. Why my mask keeps falling off, geez. Okay. It's all about quality. Today, we're going to be dealing with light. How is the lighting? And that's really what it's about, the quality. Did you match the qualities of the light? So we'll get into the qualities or the principles of light so that everybody understands what they are. But just to let you know that, you know, how you're evaluated is also inside each activity. We're going to expect that everybody can deliver a quality render without noise. It looks good. It looks professional. Because that's the goal, really. When you guys start making your demo reels, you want to have your stuff look as good as possible. Not everybody's going to be a shading and lighting artist. We realize that. But you really want to be able to present the best possible impression for an employer. You know, you're taking an art test, you want that to be killer so that you get the job. All right, so a couple of things. Naming is very important when you submit something. I used to work on the Space Coast and we used to do a lot of simulation work for different customers. Can't really say who they are. But I did a lot of scripting for pipeline work. Like I worked in what was called the integration department. So I had the modelers, I had all the other people give me stuff and I assembled the scenes. Kind of like a level, not quite a level designer, but I used to put all the assets together so that the customer would get them and everything worked. So I had a lot of stuff automated, like it would come from each department. And those files all had to be named properly because in order for it to move from one department to another seamlessly without manually doing it, you had to have naming. And if stuff was not named properly, it could not move on in the pipeline. And if, you know, somebody put an extra character in there, it would stop it. So naming is really important. Make sure, like, I don't know if you understand, but in most scripting applications, a lowercase letter is considered a different, almost word from an uppercase letter. So that means that if you put a lowercase a and it's expecting an uppercase A, it won't read right or properly, I should say. So uppercase, lowercase, numbers, underscores are fine, dashes, as I mentioned. Spaces, absolutely not. you know, on your local Mac or on your local PC, you can get away with it. But as soon as you start trying to put it into a production situation, it causes problems because a lot of applications will read that space as a break. And if it's looking for a file path, it'll think that that's the end of the file path. The Mac itself is built on Unix. So pretty interface, looks great, but underneath it's Unix, and Unix, you know, is really old, really stable. It's pretty much what runs the internet for the most part. And it reads a space, or if the space is actually in a name, it has to put a backslash and a quote in there to differentiate that it is part of the word. Unless you do that, it basically crashes everything. So just no spaces. Watermark, make sure you got everything in the template. Make sure you're delivering everything that we want. All right, enough ranting about that. Any questions? Anybody here? Everybody good? Okay. How about out there in Zoom? Any questions? All right, everybody looks pretty good. All right, so let's go on and talk about the main event, which is lighting. We talked about in the first day that you need three things to make something visible. In order to make something visible, first, you need to have eyes to be able to see whether it's there or not, or a camera to record the event. You'll also need light, and you need the light to hit something. You need it to hit an object. So without any one of those three, we don't have visibility. Now, our eyes, which basically is our camera for us in the real world, we have a couple of cameras up here. Let's talk a little bit about what we see, why we see, and how we see. And how we see has always modeled all of our devices because we build things that work for us. Meaning we need, if we want color, all of our devices have color in the monitors. Our monitors have gotten better over the years. Probably even in your lifetime, it's gotten a whole lot better. In my lifetime, it's unrecognizable compared to what it used to be. I mean, it was just dreadful. Everything was kind of blurry and grainy, and you know, you could just rub your hand near a screen and feel radiation. But here, it's maybe you might feel a little heat. That's about it. And everything is crystal clear. All right, so when we talk about light, we're talking about the electromagnetic spectrum. Now, the electromagnetic spectrum is actually the name for this entire bandwidth of energy that we know about. And it goes all the way down to radio waves, microwaves, infrared. And as the waves move up, meaning it goes from radio to microwave, the waves get smaller. The energy gets more compact. So microwaves, we're all familiar with, right? Everybody burns popcorn, you cook your food, you know, you put a hot pocket in, it's frozen inside and boiling on the outside. You burn your tongue and then you get ice. Right? Infrared, again, that is beyond, or I should say, under our ability to see that information, but it's still there. And then we move into what's called the visible light spectrum. Now, the visible light spectrum is a very, very small piece of this whole electromagnetic information that we have. We've got, a very, very tiny small piece of the pie that is kind of subdivided into different bands. And those bands represent the different colors that we see. The rainbow, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Right? Once we move beyond our human ability to see, we get into ultraviolet. The stuff you got to go out in the sun, you got to protect your eyes, you got to protect your skin. And then we move from there, we move into greater energy, which is X-rays. Still way above what humans can see, but those X-rays can penetrate soft tissue. They will show a layout of our calcified bones. That's how we make X-rays, that we can see what's going on when we have, a fracture or a break in the bone. Okay, we move beyond that into gamma rays. Now, Incredible Hulk, but gamma rays represent what we consider to be the top of the electromagnetic spectrum, because that's what our instruments at this point in time can pick up, can measure, right? There's probably other things way beyond gamma rays and probably information way below radio, but we don't have devices that can measure them, at least yet. But we're interested, when we say visible light, we're talking about this little bit of information right here. All right, now, that visible light goes into our eyes. So we're talking about, we say, oh, I see the screen. Okay, really what you're seeing is light hitting the screen, bouncing off of it into your eyes. And your eyes pick up that electromagnetic information, that visible light information, and it stimulates our retinas. Our retinas then send a chemical energy signal to the brain. The brain interprets what information was given to it by the retinas. Meaning, we get this information, we try to make sense out of it with our brains. We're taught pattern recognition, colors, shapes from birth as kids, right? Everybody's, one of these things is not like the other. You get Sesame Street, which is, a really good thing to have around for kids. But we learn to identify what we see in our world. And it took practice. We didn't always recognize what things were. We were told, hey, this is a pen. Hey, this is a bottle. So over time, we can just look at them and know what they are. So that information is all due to light hitting this, bouncing off of it into our eyes. Again, it's that kind of triangle of visibility. We've got eyes, we've got an object, we've got light. Now, our retinas are broken up into two main components. They are rods and cones. So let me just kind of give a really, really crude representation. So we have cones that are broken up into red, green, and blue. They are each responsible for that bandwidth of energy. So let's just say, for example, these are my retinas here. And around the retinas, we've got, let's go, I guess there's no really way to get gray, but, oh yeah, there is. So around our cones, we have these rods. Obviously, not to scale, but just kind of an idea to give you. All right, so this would be considered a very crude representation of our retinas, right? We got these little sensors inside, they pick up color. Around the outside, we have these things called rods. They are sensitive to the intensity of light. Their job is when their light levels are very low, they pick up our primary vision. So if you go outside on a really dark night, you'll notice that what might be really bright, brilliant, green and red colors outside, like houses, buildings, cars, everything looks very muted and almost gray. And that's because there's not enough light intensity to really trigger the cones into full processing. So the rods kind of pick up for it around the periphery of the eye. Now, there's also this thing called night vision or night blindness, where if you stare at an object directly in very, very low light situations, like your finger, it almost looks like it disappears. That's because there's very low levels of light. And what you have to do is kind of look off to the side just a little for our peripheral vision so that the cones pick it up. As long as it's a little weird sensation, but keep your eyes moving, you don't notice it. It's only when they are stationary, locked onto one thing, do you notice that kind of fade in the vision. So we've got rods, they're sensitive to light. They also kind of trigger that automatic response when you go outside and it's really bright and you kind of squint and your pupils contract. Your pupils are basically like the iris of a camera. When there's a lot of light, they will contract to let very little light in and basically keep the retinas from getting damaged. And then when it's really dark, they open up to let more light in, just like a camera. All right, having these red, green, and blue cones works really well because, as I mentioned, all of our devices are built on this model. We've got every electronic device that we own uses this RGB model of display. So it kind of matches what we see. Now you can take red, green, and blue and mix those colors together and get 16.5 million colors. That's why on our photos, stuff you download off the internet, you take on your phone, right? You've got, it usually comes out as a JPEG. You take a picture, you look at it, it's RGB, which means it's red, green, and blue. All those colors are filtered together to give us all the color variations that we're used to seeing. So even just 3 colors, you can mix and match and get what we would consider to be continuous tone, where we see color, we can see gradients in color and variations to a very fine detail. Now, when we talk about color and light, we're talking about mixing the two together. So we've got light, red, green, and blue, we mix them together. That is additive, which means we start with black. And when we add the lights together, we get white. So here I've got, my triangle here, red, green, blue. And I've got a little animation with spotlights. So you can see when red and green mix together, we get yellow. When green and blue mix together, we get this cyan color. Blue and red, we get magenta. In the middle, when all overlap equally, what do we get? What's it? We get white, exactly. So that tells us this is the additive method of color. Whereas in fine art, we usually start with a white piece of paper. We get color, we mix them together. When we mix all the colors together, we get kind of a yucky brown. We don't really get a pure black, but we get a brown. That would be called subtractive. So fine art, we use subtractive. I always think of it like you take a block of clay, you start removing what you don't want out of that to create your sculpture. Same thing with stone, with wood, with metal. You know, it's very rare that you have an additive process. Does that make sense? Anybody have any questions over in Zoom too? All right, Kentavious is good. Jacer's good. All right. Now, one other thing with this whole additive method, it's not only color that's additive, it is also light intensity. So what that means is, for example, if we've got our red spotlight and say that's got an intensity of 3, we've got our green spotlight, that's got an intensity of 3, and our blue, that's got an intensity of 3, where they all overlap together, if it's truly additive, what would 3 plus 3 plus 3 be? 9, yeah. So in theory, wherever they overlap, we would get 9. Now, that's really important when we start using multiple lights. Today, it's going to be simple, single light source. But when we start adding, well, you guys are probably familiar with the terms key light, fill light, maybe backlight, right? Where those lights overlap, they are greater, it's greater than the sum total of each light individually. So that's why it's important to kind of understand this, because when you are lighting, you have 2 lights that overlap, it's going to be brighter than where the lights are by themselves. And that's important to understand when you're trying to aesthetically create something that draws the eye to it and enhances your composition. All right, so again, very simple process here. Red, green, blue spotlights, where they overlap, we get white. You guys can do this, you know, get a couple of lights after today. Hopefully you understand where they are and what they do and how to do it. But you can take 3 different lights and overlap them and see what you get. Change the colors of them. All right. Now, we talk about color is the result of the way that a surface interacts with light, or that color on the surface interacts with light. So here in Full Sail, we've got some walls that are kind of teal and some that are gold and some that are gray. Why is it that we see those colors? What is being created? Because our light, by default, if you take a look at the ceilings, even in your homes, most of our light is whitish, right? That means it's got all the bandwidths in there. But why is it that we see with that white light, we see these colors in our environment? Yes. Yep, that's it. Very good, Frenzy. Frenzy said that the, oh, right, Frenzy, sorry, that's Kayvon. Oh, sorry. All right, Kayvon gets credit. He gets the cookie for that one. So Kayvon, right. All right, so basically, Kayvon said that you have to understand that when we have white light hitting a surface, and we see green, we see blue, we see red, those are the colors that are being reflected back to us. The other colors are being absorbed, which is what we see in this sphere. We see red because this is the primary color that's being reflected back to us. All the other colors are mostly absorbed. Now, that doesn't mean that there might not be a little bit of blue or a little bit of green in that color. It's just the primary one we see is red. So, excellent. Now, materials are daily objects that light hits to make things visible to us, can do one of three basic things. A material can absorb light, meaning it lets it in, it kind of traps it, bounces around, doesn't really let it back out to be visible to the camera. Now, obviously, energy goes somewhere, but it's not going back to the camera or our eyes. So objects can absorb light. On really smooth, shiny surfaces, objects can reflect light. Or if they are transparent, they can allow light to go through them. Depending on the kind of object that they are, that could mean that the light rays don't pass through and obstruct it, they bend or refract when they go through. So if I hold up my water bottle here, the top part is, I can kind of see through it pretty good. It's not too bad. But when I have the plastic with water, that water is making the light bend a lot more as it passes through. So now everything, I feel like an insect, like everything is just like all out of whack. So light can transmit. When light transmits, it passes through a surface unobstructed. When it refracts, it hits the surface and bends according to what the material is. Like air. Air would be an example of transmission. We really don't see light bend in air unless there's, well, here in Florida, there's moisture in it and it's hot and it causes the light to bend. You go outside and you kind of see the wavy lines of light out there, right? That's because the moisture particles are heated and they are moving around and basically kind of obstructing the light rays. Not obstructing, but kind of redirecting them around. Does that make sense? Yeah, exactly. Anybody have any questions so far? So Spencer, Nathaniel, Marie, Kentavious, Joni, Jacer, Derek, Darian, Clifton, Brian, Angel. Everybody good? All right. Everybody's pretty good. All right. So let's talk a little bit about this material property that we are using on all of our scenes. This is called a diffuse material. Now, a lot of you might look at it and go, oh, that's Lambert. But technically, Lambert is the computer scientist who wrote the code to describe what we see. as a Lambert. So what's going on with a Lambert, or I should say a diffuse material, is that we have these microscopic irregularities on the surface. And anything that we think is really smooth, if you look at it close enough with a microscope or some other high-powered device, you would be able to see all the imperfections in the surface. Nothing is perfectly smooth. I mean, there's even been really high-powered microscopic images of razor blades, which we would consider to be super sharp and super smooth. You look at it and it looks like the Grand Canyon if you look at it close enough. So to some degree or another, it depends on how small those imperfections are. The smaller the imperfections, the smoother the surface looks. The smoother the surface looks means we will get light rays bouncing off of it in an organized fashion. So for example, we have metal, we have this kind of plasticky material behind me. It's kind of like lucite or, just some kind of plastic. Might even be glass. All right, it's smooth. We can see reflections. I can see the reflections of the lights in the ceiling. But in a standard diffuse material, the microscopic irregularities are big enough where the light rays are scattered across the entire surface. They're not absorbed, they're just scattered. So instead of a light ray coming in on a really smooth surface and bouncing back sort of at the angle. So we have some ceiling lights coming in, they hit the surface, they bounce back pretty much to your eye. You can see it. You can see it because it's a result of the light hitting the surface and finding your eye. That's what we call a kind of specular highlight. Like on this little plastic object here, you can see some reflection in there. That means the direct light's hitting it and it's finding its way to your eye. Now, in a diffuse surface, it hits all those little nooks and crannies and scatters and diffuses and breaks apart. So it takes a reflection and spreads it across the entire surface. So a couple of properties of a diffuse material are you can't see any environment reflections in it. You hold it up, you can't see you can't see whatever is in your environment. You also can't see direct light highlights. We call those as specular highlights, where the light source hits the surface and then that bounces back into your eye. That's diffused and scattered so much you can't tell where the light sources are coming from. So this is really, in gaming, this would be considered to be your base material, where it's got no reflectivity, it's got no transparency, it just provides maybe color information. If not color, it's going to provide you with value, which is dark and light. Does that make sense? Anybody have any questions out there in Zoom land also? Questions? Anything not clear? Just feel free to unmute yourselves. I got earbuds in so I can hear if there's a question. You can type it in chat. Trying to keep an eye on chat at the same time. All right, so we're going to talk about this diffuse reflection because all of our materials have a diffuse section of the material. So I got three of the top contenders here. I got Arnold, I got RenderMan, and I have V-Ray. Those are really the three big ones as far as software renderers go. So you see Arnold has what's called a base, and that base color is diffuse gray. RenderMan has a separate diffuse section of the material. And V-Ray Under their basic parameters, they have a diffuse color. So everybody recognizes this is the base part of the material. Go into Unreal, create a material, everything sits on top of that base. All the reflectivity, all the various maps. Now, let's talk about, we talked a little bit about material, and that's the material we're going to be using through the first 5 projects. I lied. Next time we've actually got a little, for the portrait, we've actually got a skin texture on it for you. Just because it looks a lot better than some ghosty, dead looking, diffuse person. So we put it on there, it doesn't quite look so creepy. But that's really the only thing that's going to have any color in it until we get to materials. So we talk about light. Before we actually talk about light, let's talk about what we call the principles of light, or sometimes called the qualities of light. And this is taken from several books. I just kind of did a whole bunch of research on photography and, found that they were teaching this. And I'm like, this is brilliant. Why aren't we teaching this? They have it broken down into the basics of light. And if you follow these basics in order, it's going to set you up to succeed when you go to light something. And the first thing that you want to get is light direction. That is the most important part of lighting. Where is it coming from? Is it coming from above? Is it coming from in front, on the side, behind, below? Okay, all those things give us a clue as to what we see as far as shadows go. Because everything is a result of light hitting a surface. That surface, if light hits it, will create a shadow. So, I got my tablet pen here. If I put it on the desk or the, well, I got sort of a pulpit up here almost. Lectern, whatever you want to call it. If I put it down, I can see that there's a shadow. So you guys can put your hands down on your desks. And you should be able to see at least what I would consider to be a primary shadow. So I'll be right back. Anybody watching? So, yeah, kind of soft, but you guys can see a shadow, right? Just put your hand down. Okay. For me, primary shadow looks like it's being created on this side, my left, your right. And that tells me most of the light is coming from the opposite side, because light and shadow are always opposite each other. It's like 180 degrees. So as long as we understand that shadow will be created 180 degrees from the light source, that lets us know when we're looking at an image and we're trying to figure out where's the light coming from. Oh, I see a shadow off of the nose on the right side of the face. That means the light's coming from this side. Or if the nose shadow is pointing up, that means my light's below. Or if my nose shadow is pointing down, that means my light is coming from above. So light direction is the key. Next, light intensity. How bright is the light? So where's it coming from? How bright is it? How bright is it? Next, is there any color involved? For color, Do you notice, does it look like it feels warm? Does it feel cool? Cool being what kind of colors? Yeah, blues, greens, sometimes purples. Purple's a weird color because it has blues and it has reds in it both. We usually consider reds to be, warm. Red, warm colors, kind of like reds, oranges, yellows. And again, purple is a weird color. It could go either way. So is there color in it? If not, if it looks white, that means it's got all the bandwidths in it together. So color, warm, cool, or for want of a better word, neutral. Neutral would be kind of like our white light that we're used to seeing. Now, light in this room, I'd venture to say it verges on the warm side. It feels a little bit yellow. Maybe it's because the intensity is low, but it just feels warm rather than being cold and cool and kind of stark. So once we get through the first three, then we get into, in photography, they consider it to be contrast and hardness, but for CG, I like to call it shadow quality. What does your shadow look like? Is your shadow soft? Meaning, are the edges blurry? Like when I put my hand down on the table, my shadow was pretty blurry, right? But if I stick my shadow of my hand up here on this wall, it looks a little harder. It's not as broken up. So, hard shadows, soft shadows. That translates to soft light, which usually means big light, large light. Now, large light has to do with how close that light is to the surface or the object as well. It doesn't necessarily mean it's a huge, gigantic light the size of a building, right? It could mean that it's a small light. The object might be small, but it's really close to it. So if a light is close to something, it's going to appear to be softer than if that same light is pulled back further, because that light gets smaller in appearance. It's apparent size of the light. So big light or close light. And over here, hard light, this is going to be the opposite. Small light. Or distant light, far away. So for us in CG, I say principles of light, light direction, light intensity, light color, shadow quality. When you look at an image and try to recreate it, if you go in that order, you'll have a lot more success than going, oh my God, where do I start? Always look where it's coming from. Then, how bright is it? Is there color involved? Most of the time, no. Good, check. White light's good. Then, what do my shadows look like? Are my shadows soft and blurry? Or are they razor sharp? And that will tell you whether it's a big light or a small light. So let's take a look at the effect of that big light, small light in a simple little animation I have here. It's basically a small area light, or small in relationship to where it is positioned. It's far away from the sphere. And the shadows are not super razor sharp, but they are contracted. Now, when I play the animation, the sphere goes toward the light. As it goes toward the light's not getting bigger, but guess what? The object's getting closer to it, so the light appears to be bigger, apparent bigger size. And the shadows spread out. They get really big. And then when the sphere moves away, it contracts. So big light, soft light. You know, people say hard, soft light all the time. It's a figure of speech. They're really talking about size and position of the light. Does that make sense? Anybody have any questions out there in Zoom land? Jacer's good. Awesome. So it has, just remember, it has nothing to do with intensity of the light. All right, now we start talking about physical lights, like in the real world. Our light that we think of probably the most, whether we realize it or not, is the sun. That provides for us, we go outside, there's our main illumination. Even on an overcast, cloudy day, right, you got clouds blocking the sun, but guess what? Some of that sunlight gets through the clouds. Now, granted, when that sunlight gets through, what are clouds made of? Yeah, moisture, particles, pollution, whatever, dust particles, right? So that's going to diffuse that sunlight as it comes through. All those little droplets of water and particles are going to make that light kind of shoot around like a pinball machine. And then eventually it will come out, but it will be scattered or diffused and create a big blanket of light. That's why when you walk outside on an overcast day, the shadows are super soft. It's hard to see your shadows sometimes because it is so diffused. Now, our sun appears to us to be roughly 5 millimeters in the sky, or 5 centimeters in the sky. Millimeters too small. So, but the sun in reality is like 1,000,000 times bigger than the Earth. So it is a big, giant light that happens to be far away. Big light far away means we walk outside, our shadows are pretty hard on the ground. That direct sunlight provides hard shadows for the most part. So, let's see if I can catch that at the very end. All right, so here, that little tiny dot represents the sun. The sun is a big ball of gas that is what we call an omnidirectional light. Shines in all directions. Now, of that direction, 360 degrees, how many of those degrees do you think really reach the Earth? All right, well, 3 of the arrows, but my arrows are kind of 45 degrees-ish, right? So if that's a good point, if we extend this, that kind of misses the Earth. So obviously this one gets there. But I think you could narrow the degrees down. I think it's under 10% or 10 degrees of the sunlight actually reach the Earth. It's a very, very small fractional point of 360 degrees. Just because those light rays are being shot out into space, and it looks like they might hit the Earth, but in reality, they're not going to hit the Earth that much. We're going to get, like I said, a small portion. And that small portion of angle of light means that by the time the sun's rays get to Earth, they are almost nearly perfectly parallel. Now, what does that mean for us? Well, that usually means that parallel light rays will create for us parallel shadows. How do we know? Well, go outside, take a look at trees, fence posts, telephone poles, anything sticking up out of the ground, plants. You can see their shadows will almost be perfectly parallel to each other. So that is one very distinct feature of our sunlight. And that is also a very distinct feature that we need to have in CG, because most of our lights don't behave like that. Most of our lights will kind of fan out because they are being emitted from somewhere and they're just going to kind of spread out. Almost like a spotlight or a flashlight or car headlights. You know, even if it's a big flat area of light, that big area of light's still going to fan light out all over. It's not going to be, you know, directional, we'll call it. So that requires us to use a special light in CG called the directional light. And that directional light is designed to create parallel light rays and consequently parallel shadows. Now, the nice thing about our directional light, the icon is actually 3 parallel arrows pointing, so you know there's your sun. So for us, the directional light. Creates parallel light rays and also parallel shadows. Considered to be our premier hard light outside. Now, we talked a little bit about this, right? Not all our sunlight reaches the Earth. We're going through different layers of our atmosphere. We've got gas, different levels and types of gases in our atmosphere. We get down to the lower parts of our atmosphere where we have the moisture vapor, which clouds for us for the most part. So not all of our sunlight reaches the Earth directly. Some of it reaches it in the form of indirect or scattered diffuse light. Light that passes through a cloud, light that just kind of, you notice our sky out there is not totally black, right? It's got that nice bluish color. Well, that means that all the gases in the atmosphere are kind of being lit up by that sunlight coming through. So there's another indicator that we're getting more light than just direct sunlight coming in. We're getting it all around us. So the non-direct sunlight is considered diffused, scattered, meaning softer. That's why when you go out, as I mentioned earlier, you go out on an overcast day, all the shadows are super soft out there. Now, in addition to direct light, diffused light, we also get bounce light. So when our sunlight does come down, hit the ground, that energy is not going away. It's going to bounce off of the ground and start bouncing around in our environment, hitting us, hitting trees, hitting grass, hitting trees, hitting buildings, cars, whatever's out there. every time light hits a surface, it's going to be diffused slightly. Look at the ground, look at the asphalt outside, all those little crags and nooks and cracks in asphalt and concrete. No matter how smooth that concrete is, it's still concrete. It's got sand. It's a pretty rough surface on it. That light gets diffused every time it bounces off of something. And when it bounces off of something, it's picking up color also as it bounces off. Remember, light is a result of an object hitting a surface, bouncing off of it, and going into our eyes. That's how we see color. That's how we see light. We need light to hit something to be able to see it. Now, lighting is super important as an additional tool to really good composition, staging, right? Your light can help draw the viewer's eye where you want them to look. It'll establish your focal point. All right, so light has several roles in helping to reveal the world. We understand shapes, we understand form, we understand spatial relationship, how far away is one object to another, right? And we have common terms that we use all the time for lights, like key lights and fill lights and bounce lights, rim lights, backlights, up lights, kick lights, and even down lights. Now, some of these are just modified versions of, key and fill. But they are used as additional lights on top of key lights and fill lights. So let's take a look and see. We've got some photographic reference. A friend of mine took these. So key lights provide the main shadow source in your image. Wherever you see light on the surface, shadow is going to be 180 degrees from that surface. All right, so we got light here. So we have shadow on the opposite side. So nice thing about this, even though it's a single light, right? We got light here, we got shadow here. Well, guess what? Not all the light hits the head. It bounces, hits the wall. We got light here. And then over here on this side, we got shadow. So they kind of help separate each other. And that's something that you want lighting to do, is help to separate those different planes that we talked about. We talked about foreground, midground, background, right? That light can be used to kind of add more depth into a scene. So key light, main shadow source. Shadow is usually 180 degrees away. Now, we've also got fill lights. Fill lights, their job is to support the key. Key light can't necessarily get in to do the job completely illuminating the subject the way you want. So we use a fill light to kind of brighten up the areas that might have too much shadow. Key light, don't forget, is responsible for the main shadow source. Fill lights, you're probably not going to notice fill light shadows. At least you shouldn't, because then it gets in the way of the key light, gets in the way of your composition. Remember, shadows can be used as a compositional element, just like objects or subjects can. Those shadows can point in directions. They can provide additional interest in your scene. Now, part of the trick is when you start lighting, like, okay, I got a key light, but how bright should my fill light be? right? I always recommend for a fill light, start your fill light at 50% of the intensity of your key light. That way you've established a ratio. Key light's brighter, fill light's not as bright. Now, if 50% energy, power, intensity, whatever you want to call it, is not enough, increase it. If it's too much, lower it, but you've got a starting point. Okay, again, it's a starting point. Too much, knock it down. Not enough, increase it. Now, a lot of times, instead of a fill light, we might use something, a separate light. We might use what's called a bounce light. And a bounce light is simply a light being projected or aimed at a surface and then using the light that bounces off of that surface to help illuminate our subject. One of the advantages of it is it provides usually a much softer diffused light, meaning it just looks more natural. So here we've got light coming in from the right. There's our key light. In this case, happens to be coming from a window nearby. We have what's called a bounce card or a reflector on the other side, bouncing some of that light from the window onto the subject on the left. And it has a slightly different look than just using a separate light. Usually looks a lot softer. There's always a much less noticeable gradient between the really bright light, that's the key light, and then that bounce light. So we have light source here. We hit our reflective surface, bounce card. We go back to the subject. What kind of surface can you use? You can use anything, really, as long as it provides the look you want. Anybody ever use foam core? It's kind of like poster board. It's got rigid foam in the middle and it's got cardboard on top and bottom. Okay, so usually it's smooth on one side, not quite as smooth on the other. That makes a really nice bounce card because it's light in color, usually the white ones. And you flip it over and it's a little bit rougher paper, so it diffuses the light a little bit more. It could be one of those car shades that you have put in your window in Florida so it doesn't destroy the inside of your car and make it like 300 degrees. Anything will really work. A lot of times in film and photography, they have dedicated objects they use as bounce cards. They have reflectors. Some of them look like they're foil. Some of them look like umbrellas, that kind of material. Some of them look like our screen. That's a really good because it's got kind of like little silver particles in it. Makes it nice and reflective, but diffuse at the same time without too much glare. So anything can really do as far as creating bounce light. So here's the caveat though. Caveat being there's always a what if or a but. In CG, we really don't have a 1-to-1 energy ratio that we have in the real world, meaning our lights don't produce as much energy and travel as far as light does in the real world. So whenever there's a bounce card involved, we usually use a second light source, if that makes sense. Now, we're going to talk about that need when we get into doing the portraits on Friday. Right now, we're just going to use a single light source for today. But this is kind of creating the background for when we get to multiple lights on Friday. All right, anybody have any questions? Everybody good? All right, so Brianna, Javon, right? Tavon. Okay, I'll get it. Sorry. Tavon and Chanel and Frenzy. Tavon. T. My friend has, my son has a friend called Javon, and kind of remind me of him, so sorry. Okay, well, that I might be able to remember. All right, but Tavon, got it. How about out there in the Zoom universe? Anybody got any questions? All right, Cantavius is good. Angel's good. Brian, any questions? Marie's good. Thank you. Spencer, questions? Nathaniel? Nathaniel's good. Thank you. All right, if you do have questions, just type them in, hit the space bar to temporarily unmute yourself. All right, let's talk a little bit about another style of lighting called rim lighting. Sometimes this is also called backlighting, but technically it is different. Now, a rim light is used when you want to separate or help separate the subject from the background. Now, in this instance here, we got Gary Sinise, actor, and typical kind of 3-point lighting headshot. You've got a key light, which we can tell there's key light coming in from the right side. Okay, we probably have a little bit of bounce light or fill light here, not completely dark, got a little bit here on this side of the face. All right, so that tells us this is fill. So we got key, we got fill light here too. But the problem is the subject has on a dark shirt. The background that our subject is in front of has what's called a gradient background. It's usually, the background screen is usually angled away from the subject so that it gets darker the further away from the subject it goes. It's a very simple gradient that most photographers use. Right? But the problem is that dark background in the lower left corner will cause the shirt to blend in with the background. In order to avoid that, we use a small, bright light behind the subject, usually opposite the key, and we aim it at the back of the subject so we get a little bit of edge or rim of the subject illuminated, very small, bright light, so that now our subject has that little edge of illumination, that rim, and that helps to keep the subject forward and not have him blend in with the background. So we got the rim back here. So key light on the right. Remember, fill light is probably going to be on the opposite side of the key. That's usually pretty easy to remember. And then if we find the subject blends into the background, we can use a rim light to help separate them. That makes sense? Everybody good? All right. So, you know, here, crime dramas, they use them all the time. CSI Miami. whenever they're doing something meant to look really important, they've always got, a rim light on the subject. A lot of times in the interrogation room on all those crime dramas, they always have a rim light, bright, super bright light behind the subject, illuminates the hair, makes everything light up, get the edge of the subject just to help separate them from the backdrop. So there is another option to a rim light, and that would technically be called a backlight. A backlight is usually aimed away from the subject at the wall or the backdrop behind the subject, so that the wall's illuminated, the subject is illuminated, and you have separation. Now, we'll get into that when we talk about portraits on Friday. But typical backlight is really behind the subject and used mostly, especially in film and drama, to create a lot of tension. So here on the right side, the man who wasn't there, 2001, Coen Brothers film, kind of an homage to what's called film noir. Dark film, black film. In French, it really has to do with the seedy side of humanity, all the vices and things that humans love that are no good for us or are illegal. So crime dramas, basically. So really popular in the 1940s and 1950s. I believe the big combo on the left here was 1944. This was done by kind of the father of film noir. His name was John Alton. A-L-T-O-N. He wrote a book called The Principles of Light. And he described his technique for lighting. And they came up with this whole backlight as a way to tell the story and have the lighting to be as dramatic as the dialogue and the acting. And this is really where this whole film style came from. But what they did was they found when they put a light behind the subject, put the subject in front of the light and then the camera, they got a silhouette, which made for very interesting staging. If you stage it correctly, you'll see, you don't need any action or even any dialogue. You can set up what's going to happen. They also found that instead of just putting the light behind the subject, put some smoke or steam or fog between the light and the subject. It created a really interesting kind of cloudy backdrop. Now, filmmakers like Alfred Hitchcock and the Coen brothers used backlighting also as a way to kind of set up a expectation for the action that's going to follow. And I'm thinking of, if anybody's ever seen Psycho, Alfred Hitchcock's movie. It's got supposedly the famous shower scene where somebody gets stabbed in the shower and you see the blood go down the drain, and it's a murder mystery. But they show a silhouette of the character before it happens. Here, anytime you see a profile of somebody and there's another person in the bathtub, usually in the next scene, it's not good what happens to that person in the bathtub. It's kind of like a foreshadowing or a little bit of a, precursor to what's going to happen. And again, that's all film noir. So that is true technical backlighting, where subject has the light behind them, the subject is between the light and the camera. Now, uplight, sometimes called kick light, that comes from below. First used in the 1920s for horror movies. They would light the evil character from below. Same thing as you taking a flashlight, you go out, you got your siblings or family, and you tell scary stories. You put the flashlight into your face. right? Because light usually comes from above, so it's kind of jarring to see it come from below. It sets up an expectation. Now, a kick light is a little bit different than uplight. A kick light is usually on the subject to accent a part of the subject beyond. It's not meant to get in the way of the key light. It's just meant to draw attention or subtle attention to something else. Like maybe there's something in the pocket, or if you've got a character with armor on, you have a highlight on that area and you want to draw to the fact that that's where they have their sword, or they've got a special weapon, or they have something else. So usually accent features of your subject. Your subject doesn't have to be a person, it can be an object. Downlight, light coming from above, we're used to seeing this all the time. Outside, we've got sunlight. Most of our interior lighting is from above, right? But in film, you can use it artistically. Like in the middle here, The Godfather, Francis Ford Coppola, used it to shine a really bright spotlight on Marlon Brando's forehead, and that made the eyebrows shadow over the eyes, so that it made the character look a lot more soulless than he was when he was doing business in the library. So it's all about using light to help tell the story, unspoken part of the story. Does that make sense? So all these tools are at your disposal when you are the artist, and more. You're limited by your imagination, really. But once you know the basics of lighting, then it's just like anything else. You are free to experiment to your heart's content. Now, a couple of things here. On the left, we've got Toy Story 1. Now, the reason I like to bring up Toy Story is because for me, this is really the reason I got into 3D. Before that, I was just a happy graphic artist, plugging away, doing advertising and stuff. And then I saw that and I was like, what am I doing? Why am I in 2D? So it also represents a milestone for us as 3D artists, because it is the first full-length motion picture film that was done in 3D. Up until then, there had been shorts, there had been small experimentations, but nobody really did a full movie. Does anybody know what year Toy Story came out? Ooh, you're close. Ooh, you're really close. There we go. Clifton said it right here. 1995. Yes, Toy Story 1, 1995. So when it was released, when did they start working on it? Well, probably around 1990, to be honest, because it took a while to make. And probably even before that, they had the idea floating around. Now, the reason I bring that up is because in 1995, I would venture to say most, if not all of you, were not even born. But you may have heard stories about what life was like back in the old dark ages, right? Like cell phones. Cell phones were giant, huge bricks full of radiation. And they weighed like 2 or 3 pounds. They were more like blunt objects than they were actual, devices to communicate with. 1995 give you just a little bit of perspective. Today, we measure storage on our computers in gigabytes and terabytes, right? Back then, you were lucky if you had megabytes. So megabytes was probably the big storage then. That was huge. But most of us had like kilobytes and bytes. Like you had these small, well, they weren't small, but these floppy disks. They called them floppy because they were actually soft plastic. They held kilobytes of information, which for you guys would be probably 1/4 of like 1/10 of your phone screen would be that if I had to put it in a size, maybe even smaller than that. Smaller than that, because most flash drives are still in megabytes. We're talking under megabytes. So megabytes, top of the line storage, but for the most of us, it was kilobytes and bytes. Bytes being really, really small. All right. What else going on? Oh, Windows 95 was introduced. The Mac OS as we know it did not really exist. It was the old Mac OS version, which did not have what's called a multi-finder. That means you could only have one program open at a time. You had to quit out of it, go to the desktop, launch another program. You couldn't switch between applications. You couldn't see the desktop and your program that you were working on at the same time. Primitive, right? Very primitive. So they realized at Pixar that in order to create a movie that people could relate to, they needed to have basic, relatable movie expectations, which means they had to provide good lighting, characters that people could relate to, as well as a good story. So technology was limited. In fact, everybody in this room in Full Sail, there's 5 of us in here. Our cell phones could probably render a frame of Toy Story quicker than the top of the line computers could there at the time. So they realized that they needed good lighting. And in order to create good lighting, they needed to have at least a minimum set. So they would have a key light, and they would have a fill light. They could use a rim light. When all the lights were added together, remember, lighting is additive, so all these intensities add up. We got the finished product, Woody. Doesn't sound very magical, but hey, that was a big deal at that time. If you take a look at, has anybody not seen Toy Story? Frank said he paid $189 for a 4 megabyte RAM. Huh. So anybody, if you haven't seen Toy Story, watch it. Okay, it looks a little dated now, but it still holds up. We're coming up on almost 30 years. So it still holds up because the story's good and the characters are relatable. And they did a good job with the limited resources they had creating a good story and a good film. Now, fast forward to the next Pixar release, which was Bug's Life. Anybody know what year? Too high, too low. 2001? Nope, wait, it's earlier than that. 96, Clifton, you're a little low. 1998. All right, so technology got better. We've got more lights to light flick up, right? We got a key light. They've also got a really kind of low level fill light. You got a rim light coming from the right side, or actually it's left rim. Then we got a right rim. Then we've got a kick light coming up from the floor, getting the side of the head here. We've got a little bit of bounce light coming from below. And all together, that's the final look of Flick. Now, in the original Toy Story, 3 years earlier, there were very few scenes where there were lots and lots of characters on screen at once. The only thing I can think of in that story is when they're in that machine where all the aliens are, and that little gumball kind of machine where the claw would come down and pick them up. But most of them weren't moving. There were only a few that would move or blink at the same time. That was because the technology was not advanced enough where we could have that much sophisticated action and be able to render the frames out in a reasonable amount of time. It was primitive. But in Bug's life, there were a lot of firsts. One was, it was the first time that there were 100 animated characters on screen at the same time with their own action. It's a scene where Hopper comes down into the ant colony. He's terrorizing the ants because he wants food, right? He looks down one of the tunnels and there's like 100 little Flicks all there going, whoa, moving around all with their own action. That was a big deal. It was only a brief, 1 or 2 seconds, which equated to about 48 frames. But that was a big deal. Another was visual effects in an animated feature. So again, it's Hopper, Flick, they're outside at night. All the ants had made this kind of wooden bird and put it on fire, and we're trying to scare away all of the grasshoppers, Hopper's clan. And what happened was he found out, so he and Flick got into a fight. He's kicking the crap out of Flick, and behind him there's a fire where the bird is burning, and you can see flames and smoke and sparks all going up. That was a big deal because that was visual effects in a movie. So, it doesn't seem, looking back at it, that it was that incredible, but at the time that was technologically pretty advanced. 1998, we were still in megabyte territory. Clock speeds on computers, we were, megahertz, maybe going into gigahertz speed, but still slow. Storage, still megabytes. Gigabytes were pretty unheard of. Able to have more lights, able to have more complex effects going on. 3 years made a difference. And every subsequent film, whether Pixar made it or not, always stood on the shoulders of what came before. So all the things that we take for granted today were all worked out through blood, sweat, and tears to get to the point where we've got laptops we can run Maya on and be able to render out almost film quality images on a laptop. So the reason I mention that is because whatever your limitations are, whatever your requirements are for the job, there's always a way to be creative about making it look like there's more than there really is. It's all about that artist in you where you can make things look better. Does that make sense? All right, so we talk about mood and lighting. We talked about film noir. The reason I mentioned film noir is because for today, you guys will have a chance to do a My Comp again once you get done doing the 4 requirements that we have for the lighting exercises. You guys will be able to find some, lighting reference, as long as it has only a single light in it, be able to recreate it. But film noir makes a really good reference because it often looks or is done with a single light source. and it uses shadow and light effectively. That whole light, dark scenario. So a lot of these look like they could be one light. Some of them are. Most of them are not, though. But it makes a really good reference as a starting point for somebody trying to figure out, how do I make something look good with a single light? All right, this is a good chance to take a break. Anybody have any questions before we go on a short break? All right, short break. We're going to take 20 minutes, just like we did on Monday. Gives me a chance to render out the first part of lecture so my computer doesn't fill up. I can usually upload it in time, and we'll get back here. So let's see, what time is it? So by the time we get out of here, it'll probably be 11. So come back at 11:18. We'll pick up, we'll do some demos. We'll talk again about the principles of light. We'll talk about light intensity versus exposure, which we have exposure controls in the lights and why we don't use them. Then we'll get into demoing the simple directional point, spot, and the Arnold area light. So, anybody have any questions in Zoom before we go on break? All right. So, I'm going to stop the recording.